How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at ideal gas laws. So objectives being to solve ideal gas law problems using the PV equals nRT equation. All right, so what is an ideal gas? It's a gas that behaves exactly like gases are supposed to. Their molecules aren't attracted to each other at all. Their volume of the particles themselves are so small that we just say it's zero. And do all gases behave ideally? Most of the times with the problems that we're going to be looking at, yes. But most gases actually do have some very small attractive forces. And the particles, even though they're very small compared to the volume of the container, they do have their own volume. But it's generally a safe thing to assume that gases behave ideally. We'll get more into how real gases behave later. Helium is a good example of an ideal gas. So quantifying properties of an ideal gas. First, let's recall this equation from earlier. We got PV over NT equals some constant R, right? P is pressure, V is volume, N is number of moles, and T is temperature, and it's got to be in Kelvin. And then R is our gas constant. And the number for R depends on what units we're using for pressure and volume. For example, if we're using liters and atmospheres, the gas constant is 0.08206 liter atmospheres per mole Kelvin. If instead we were using pascals and cubic meters, we'd have 8.314 cubic meters times pascals per mole Kelvin. If we're using liters and torr, we'd have 62.36. But we also hate fractions. So this equation up here with this fraction, let's rearrange it to get rid of these fractions. So we got PV over NT equals R. But if I times both sides by NT, I end up with PV equals nRT. And this equation is called the ideal gas law. Right? Another common and related equation that we've seen before is the combined gas law, where P1V1 over T1 equals P2V2 over T2. And where did that equation come from? Well, we know that if we rearrange to solve for the gas constant times the number of moles, which in the combined gas law problems, the moles usually doesn't change. R is always a constant. We end up with PV over T equals some constant number. So even if we change pressure and volume and temperature, they still have to equal the same constant when it's set up with like P2 V2 over T2. Has to equal P1 V1 over T1. All right, so we got Pivner. PV equals nRT. Sample problem, what volume does 1 mole of an ideal gas occupy at STP? So STP stands for standard temperature and pressure. Standard temperature is 0 Celsius or 273 Kelvin, and the pressure is 1 atmosphere or 760 torr or 101.3 kPa, depending on what unit you're working with. R, let's use atmospheres. All right, I'm personally a fan of atmospheres, so the R constant that I'm going to use is 0.08206 liter atmospheres per mole Kelvin. Let's set it up. So if I'm trying to solve for volume, I want to divide each side by pressure so that I get volume by itself, and I end up with volume equaling nRT divided by P. So you look to my problem. I got 1 mole, that's my N. I have R, I'm using atmospheres, and liters, so it's 0.08206. Temperature at standard temperature is 273 Kelvin, and my pressure is 1 atmosphere. So when I plug and chug, I get 22.4 liters. This is what we call the molar volume of an ideal gas. It's what is the volume of 1 mole of an ideal gas at standard temperature and pressure. 22.4 liters. So 1 mole of any ideal gas at STP will take up 22.4 liters of volume. Doesn't matter what the gas is, the ideal gas, it could be hydrogen, could be helium, it doesn't matter what the identity of the gas is, 1 mole of it at STP, 22.4 liters. Example problem. A reaction that produces a gas is performed and the gas is collected. The gas is collected in a 250 milliliter flask, and after the reaction, 1.3 atmospheres of gas was collected at 31 Celsius. How many moles were created? So again, I'm going to go, all right, well, I know PV equals nRT. And the question is asking me to solve for N, so divide both sides by RT. And I get the number of moles is going to equal PV over RT. So now let me see. My pressure, they told me is 1.3 atmospheres. My volume, let's see, they said 250 milliliters, but I need to convert that to liters, so I divide by 1,000, and I get 0.250 liters divided by R. Well, if I'm using atmospheres, I'm going to have to use that 0.08206 liter atmospheres per mole Kelvin, and then times by my temperature, which has to be in Kelvin. So I convert that 31 Celsius to 304 Kelvin. Now when I get my handy dandy calculator and I plug and chug, I get 0.013 moles. So I ended up with 0.013 moles of whatever the gas was. Another example problem. A balloon is inflated to 6 liters at sea level, which is 1 atmosphere, and released. It floats into the sky until the pressure drops to be 0.45 atmospheres, and the temperature drops from 22 Celsius to negative 22 Celsius. What is the new volume of the balloon? All right, so a couple of things to consider here. The number of moles of gas is constant here. So if I have like PV equals nRT, well, N is constant, R is a constant. So let me rearrange to get those things by themselves. I divide each side by T. Now I have a new set of pressure and volume and temperature conditions, and they still have to equal N times R. So P2 V2 over T2 still equals my moles of gas times the constant. So I can just use the combined gas law to solve. So which one am I asking for? New volume. So I'm trying to get V2 by itself. So let me times each side by T2. Cancels that out. Divide each side by P2. And I get V2. I'm just going to rewrite it over here. V2 equals T2 times P1 V1 over P2 times T1. So now I can do my plugging and jugging. My new temperature is negative 22 Celsius and needs to be in Kelvin. When I do that math, I get 251 Kelvin times my initial pressure, which was 1 atmosphere, times my initial volume, which was 6 liters, divided by, let's see, P2, my new pressure is 0.45 atmospheres. And my initial temperature is 22 Celsius, which when I convert to Kelvin is 295 Kelvin. Now I can pick up my handy dandy calculator, plug and chug, and I end up with 11.3 liters. Cool. So yeah, summarize. Can you solve ideal gas law problems using the Pfiffner PV equals nRT equation? I hope so. Hope you found it helpful. See you in class. Goodbye.